Hello and welcome everyone to EC 3030. So in this video lecture, we will take a look at static random access memories. So in the previous video lecture, we have seen an overview of the memory hierarchy. In this lecture, we will see how an SRAM works. So this is the memory hierarchy in a modern microprocessor. So we have many cores, and in this course we have these registers over here, and then we have multiple layers of cache. For example, L1 cache, L1 cache, L1 cache, then L2, L3 cache, and then we have main memory, and then we have the secondary storage, and then finally we have the tertiary storage. So the secondary storage is either solid state hard drives which are based on flash or magnetic disks. The main memory is composed of DRAM. Now L3 cache is made of DRAM, where L1 and L2 cache are made of SRAM, and of course the registers are made of SRAMs. So as memory primitives, we have 4 different device technologies. So one is the SRAM, static random access memory, then we have the DRAM, dynamic random access memory, then we have flash and solid state memory, and then finally we have magnetic disks. So this is what we have seen in the previous lectures. So another thing that we looked into in the previous lecture was we just said that in the previous lecture is that SRAMs are extremely fast while they are very expensive in terms of area. And for DRAM, its access time is slower than that of SRAM, but they are dense, meaning that their area, it takes less area to make one DRAM cell. And the magnetic hard drives are extremely small, so area wise they are very efficient, but the access times are actually very large. So this is how the different memory technologies look like. So in this lecture we will see how the SRAM works, and based on that we will also try to understand why the density of SRAM is very low while the speed is the highest among all the different memories. And also we will see why SRAMs are non-volatile. Non-volatile means that if you turn off the power, the SRAM cell loses all its data. Alright. So first let's try to understand what this term random access memory means. So random access means that if you have a memory device, for example, say you have a 128 megabyte memory, and you want to access, so 128 megabyte the memory, each of these data bits or bytes have a unique address. The term random access means that if that memory is random, can be accessed randomly, that means that if you just give it the physical address, you will be able to retrieve that data readily. So essentially a RAM allows the data items to be read or written in almost same amount of time, irrespective of their physical location. In other words, wherever the data is physically within that memory device, you will be able to retrieve it or write it almost at the same time wherever that data bit is. This is in contrast to other types of data storage. So maybe serial access data storage or different kinds of direct access data storage, where the time required to read or write depends significantly on the physical location of the data on the recording media. And the examples are magnetic hard drives or rewritable CDs, DVDs, or very old magnetic tapes. So in the magnetic tapes, for example, all the data are written in a serial fashion. So if you have to retrieve a data somewhere in the tape, you have to read all the previous data maybe in a block or so. On the other hand, in a RAM, in a random access memory, you can access data, any data, randomly, and wherever this data is, you can retrieve the data uh, almost at the same time, or write the data, the amount of time to read or write the data irrespective of where that is almost constant. So what is important for a RAM is that the memory or the data bits are written in a 2D array. So for example, this is an architectural view of the memory cell, not the memory cell, the entire memory array. So say you have a certain number of columns here, say 1, 2, 3, all the way to say 2 power x. On the other hand, you have, so these are, you have 2 power x, no, you have x columns, and then you have say y number of rows. All right. So say you want to, so for example, here you have a data, you want to retrieve it, and what you give the memory is its address and also the information as to whether you want to read or write the data. So basically the address or the information that this entire memory block, entire memory device receives from the CPU is an information that looks like this. All the way to, so it receives an L bit information. So say for example, out of this L bit information, first k bits tells you which column the bit is in. So you give this address and it takes this k bit information into the column decoder, and then it selects one column over here, which is shown by this dashed curve, dashed line, and the rest of the bits from AK to AK plus 1 to AL minus 1, say this is like AL minus 1, so goes to the row decoder, and then it selects this row. So by this two select lines, what you have done is that you have selected a cell, and then the data from this cell will go into this region, this block here, and depending on whether you read or want to write this data will be retrieved from this cell or be written in this cell. Now a cell may be a single bit or a number of bits, and if it is a number of bits, then it's a word. Or you can also read or write multiple words at the same time. It depends on the architecture that you are using here. All right. So again, this 2D array is the memory, and to read or write you need this interface, which is this column decoder, row decoder, and the read write circuit here. So you need read, write, and other controls. Then also you need the address, which is this address over here, and then you have the data lines. Now this data lines is bidirectional because you use the same data bus to write into the cell or get the data and put this data back to the CPU. All right. So this is a quick overview of what a random access memory is. All right. So now let's look at the static random access memory. Now the basic structure of a static random access memory or an SRAM is very simple. It's basically two inverters connected back to back, and the output of the second inverter is connected to the input of the first inverter, and the same connection can be also be shown like this. All right. So now let's think about it. say you have a 1 over here or a 1 over here, then this will put a 0 at the output of this inverter, inverter 1, and this, so this is inverter 1, this is inverter 2, this is inverter 1, and this is inverter 2. Now this gets a 0, so this will output a 1 over here or a 1 over here. So this will input a 0 over here, and this 0 will again create a 1 over here. So now you can clearly see that there is a positive feedback here, meaning that if there is a 1 here, there is a 0 here, and this gives 0 gives a 1, and essentially these two inverter cross couple inverters will provide a basic mechanism for remembering its input or the data bit that it wants to store. Now similarly, say you have a 0 over here, so I'll just write the 0 inside a circle. Say you have a 0 over here. Now this inverter will give a 1 at its output, and if the input to the second inverter is 1, so this will give a 0 here, and this 0 will again give a 1 over here. So again, in a cross coupled inverter, because of feedback, it can remember what the memory state is. In other words, it can store a bit of data. So this is the basic building block of a static random access memory. So now let's look at how a SRAM cell looks like when you implement it with transistors. So now this is, if you take this circuit over here, it will simply look like this. So this inverter is like this, and this inverter is this. So you have a simple inverter circuit like this. However, what we usually do is we usually draw this circuit a little bit differently. So what we do is we move the first inverter to this side. So if this is inverter 1, so this is inverter 1, and if this is inverter 2, this is inverter 2. So we have just reflected inverter 2 and pushed it to the left, and inverter 1 is pushed it to the right. Now the input of inverter 1 is connected to the output of inverter 2, so which is this line over here, and the output of inverter 1 is connected to the input of the inverter 2, which is given by this line, and then this is the output of the inverter 1, and this is the output of the inverter 2. And note that inverter 1 is always an inverted version of the output of inverter 2, right? Okay, so now this is the full circuit diagram of the simplest possible SRAM circuit. So again, this is what we have seen in the previous slide. Now in addition, we have two transistors over here, one over here and another one over here, and these transistors are called pass transistors. Pass transistors, and if you count the number of transistors in this circuit, you have 6 transistors, and that's why this cell is called 6T transistors, where this T stands for transistors. Alright, so now what does these two transistors do? Now note that these two transistors, the gate of these two transistors are connected to a line over here, and this line is called the word line, and then the source terminal of these two transistors are connected to two lines. Now this transistor is connected to the line which is called bit line, and there is a straight line over it, which means that it is bit line bar. On the other hand, this the source of this pass transistors is connected to another line which is called bit line. Now this word line and bit line are used to select a SRAM cell and read and write into the SRAM cell in an array architecture. So let's take a quick look. So this is how an SRAM array looks like. All right. So here you have cell number 1 1, 1 2, 1 3. This is the row, and this goes all the way to 1n. So there are n number of cells in this row, and similarly in the same column there is 1 1, 2 1, 3 1, and this cell, for example, goes, this column goes till, say, for example, n1, and similarly n2, n3, and here it goes 2n, 3n, like this. So you have an array of n cross n SRAM cells in this array. Now, for example, you want to select this cell number 22. Now what you will need to do is put WL into VDD, and if you put WL to VDD, so if you put VDD, then you will turn on this transistor over here and this transistor over here. So what does turn on mean? Means that these transistors now can carry current, and essentially what will happen is that this output from this SRAM cell, output terminals of this SRAM cell VO1, so VO1 and VO2 will be connected to the bit line 2 and bit line bar. Okay, so now note that if this WL2 is connected to VDD, all the pass transistors in this row will be on. Now how do I make sure that I read just this cell? And to read this cell, what you will need to do is, then you just sense the voltage at these two bit lines, and if you sense these two bit lines, you will be able to read just this cell. Or if you want to write something, you will put the appropriate voltages in this 2 bit line, and as a result you will be able to write into this SRAM cell. Now in the later slides we will say as to how we actually read and write into SRAM cell, but what we are just trying to do here is to understand how to access a single cell in an array. Now note that when you are, so to read or write into this cell, you activate this word line by putting a voltage VDD, and that turns on these two transistors and also these other transistors. But you read this cell through this bit line 2 and bit line 2 bar. Now note that when you want to read this cell, you do not activate WL2, meaning that WL1. So WL1 will be at 0, WL3 will be at 0. So what will happen is that for this cell, these pass transistors will be off. So this bit line 2 bar and bit line 2 will not see output from this cell. And similarly, because WL3 is 0, these two transistors will be off as well. So bit line 2 bar and bit line 2 will not see any output from this cell or this cell. And similarly, when you are trying to write into this cell by changing the voltages of BL2 and BL2 bar, it will just write in this cell. It won't be able to write these cells because these transistors are all off. All right. Okay, so now let's look at how we can write into an SRAM. So say you want to write a 1. All right. So when you want to write 1, so let's say when you want to write 1, essentially what you want to do is you want the VO1 to be equal to VDD and VO2 to be 0 volts. All right. So for that, what you will need to do is you will put word line to VDD. As a result, this transistor will be on and this transistor will also be on. and then you will put bit line to bit line voltage to VDD and bit line bar voltage to 0. So if you put VDD over here and 0 over here, then essentially this VDD voltage will force the output here to be 0, and also this bit line is 0, bit line bar is 0, so both of them will force this VO2 to be 0, and as a result when VO2 becomes 0, this will put a 1 here, and as a result it will again this VO2 is 0, so the output of the inverter 1 will become VDD, and this way you can write a data of 1 into the SRAM cell. Alright, so now let's say you want to put a 0 into it, and in this case your VO1 should be 0 and VO2 should be VDD. So again, to do that, so you in this previous case you were writing data equals to 1. Now let's say you want to write data equals to 0. In this case again you will put word line to VDD, and in this case here now you will put bit line to 0 and bit line bar to VDD. Okay, so now you are putting bit line to 0 volts and bit line bar to VDD. So I'm just circling it to make the case that to distinguish that in this case we are writing a 0. So if you put 0 here, the input to inverter 2 is 0, so output here will be 1 or VDD, and since VDD the input to inverter 1 is VDD, then output of the inverter 1 will be 0. So essentially by the cross couple action you will get a 0 data stored in the SRAM. Alright. Alright, so again let's look at how this works. So you want to write, for example, a data of 1, so you put WL2 to VDD and WL1 to 0, WL3 to 0 and all the other word lines to 0. Okay, now essentially means that this is off, this is off, this is off, and this is off, and you want to write a data equals 1, so you will put VDD over here in this bit line and you will put 0 in the bit line bar, and as a result at this node you will get VDD and at this node you will get 0, and essentially this cell will store a data 1. So you wanted to write a data 1 into this 2 cell. Now note that this bit line is shared by this cell 3-2 and 1-2, but this bit line voltages will not be able to store any data in cell 3-2 or 1-2 because these transistors, these pass transistors, are off. Alright, now let's look at how the read works. Now first we will explain how the read works in a very simple manner. So in case you want to read a certain cell, of course what you need to do is put the word line again to VDD, right? So such that these pass transistors are turned on. Okay, so now what you will do is you will put a voltage at bit line bar and bit line. So both these bit lines will be pre-charged at a voltage of VDD. Alright, okay, and then you turn on the word line put the voltage of VDD in the word line such that these two transistors are on. Now what will happen is that if, for example, you have a data of 1, if you have a data of 1, then you will get a VDD over here and you will get a voltage 0 over here, and as soon as this transistor turns on, what it will do is the voltage at this line will start decreasing from VDD towards 0. Why is that? Because if the output here is 0, that means that this pull down transistor is on. As a result, this transistor will try to pull down this voltage towards 0. It will take some time for this voltage to go down to 0, but eventually it will start decreasing. On the other hand, this voltage line over here, this bit line over here is already at VDD, and this voltage is also VDD, and as a result what will happen is that this line will remain at VDD. So again, if the data is 1, then the voltage at the bit line bar will start going toward decreasing. On the other hand, the voltage at the bit line will stay constant at VDD. Now if you just compare the voltage difference between bit line and bit line bar, you will see that the bit line bar will be less than that of the bit line, and that way you can know that the data stored in this cell is 1. Alright. Now similarly, for example, say you have a data that is 0. Now if the data is 0, that means that the voltage at this node is, the output of inverter 1 is 0, while the output of inverter 2 is VDD. Now again what you do is both the voltages are, both the bit line and bit line bar are pre-charged at VDD. Alright, and then you apply a VDD voltage to the word line for which this transistor turns on. Alright, so now this bit line voltage is VDD and the output of inverter 2 is also VDD. So basically this bit line 2 voltage will remain constant at VDD. Alright, on the other hand, this is 0 and this is VDD and this is on. So as a result what will happen is that now the voltage at the bit line will start going down. Now again bit line bar voltage will remain constant at VDD, where the bit line bar voltage will remain constant at VDD, while the bit line voltage will start going down from VDD towards 0. Now if you can simply compare the voltage difference between the bit line bar and bit line, you will see that if the data stored is 0, then the bit line voltage will be larger than, bit line bar voltage will be larger than bit line voltage. Alright, so if we summarize, then if the data stored is 1, then the bit line bar voltage will be smaller than the bit line voltage. So VBL bar will be smaller than VBL. On the other hand, if the data stored is 0, then the voltage at the bit line bar will be larger than the bit line voltage. Alright, so this is a very simple way of explaining how the SRAM read works. Okay, so now again let's look at the array level description. Alright, so say you want to read the data of 22, cell 22, then what you will do is you will pre-charge both bit line bar 2 and bit line bar to VDD. Alright, and then you will put WL2 to VDD and all the other word lines will be 0. Okay, So as a result, this will be turned off, turned off, turned off, and turned off. Only these are turned on. All right. So now then, depending on what the data stored here in this cell 22 is, the bit line, the voltage of bit line 2 bar and the bit line 2 will change. The way it will change depends on the data that is stored in cell 22. Now again, the data stored in data stored in cell 32 or 12 will not affect the voltages of BL2 bar or BL2, simply because these pass transistors are off. So whatever the voltage is inside this cell will not affect these bit line voltages. All right. So now finally let's get back to this comparison, and let's try to understand again as to why SRAM is very low. It's very less efficient in terms of density, and you can readily understand because SRAM, there are 6 transistors in one cell. It is very big, meaning that it takes a lot of area to make one SRAM cell. You will later see that DRAM requires just one transistor and one capacitor, and flash requires just one transistor, and the magnetic memory takes one small magnetic bit which is extremely small. So essentially SRAM requires at least 6 transistors, and this is why the density of SRAM is very low. On the other hand, the speed of SRAM is very high. Now we did not talk about the speed or the access time SRAM in this video lecture, and we will not be talking about that in this class, but the idea is very simple. The idea is that because you have transistors, these pass transistors and all the inverters, so transistors are extremely fast, and because these transistors are extremely fast, you can read or write into the SRAMs very fast. On the other hand, you will see that in a DRAM, although you have one transistor, the read and write are much slower compared to SRAM, and that is because it has to do with a capacitor charging and discharging, and this is why DRAM is slower than SRAM. And then in flash, it requires a few different physical mechanisms for which is extremely slow, and magnetic RAM and the magnetic hard drives, these are even slower, of the order of milliseconds, and that has to do a lot with the fact that the access mechanism is not random, and as well as it requires physical movement of the magnetic disk. And finally, the non-volatility. You can readily see that SRAMs are non-volatile, meaning that as soon as you turn off the power, the data stored in it will be lost. And the reason is very simple. If VDD goes to 0, then all these voltages at the output and input will go to 0. So again, when you power up the system, you will have to write all the data into the SRAM array. And you will also see that DRAM is non-volatile. On the other hand, flash and magnetic hard drives are non-volatile. DRAM is volatile, flash and magnetic disks are non-volatile.